Hey team, Andre from High Performance Academy here. Welcome to another one of our members webinars. Today we're going to be touching on a topic I get asked about just about every time I do a webinar, and that's about the techniques used for road tuning. What is road tuning? Can we expect to get reasonable results on the road if we don't have access to a dyno? So we're going to dive into all of that. We'll talk about some of the pros and cons and some of the techniques and software that are available to make your life just that a little bit easier. Before we get into that though, just a few things that are going on around here, and we do have a fair bit on the go at the moment. So I've got some engine bits here, I've got some turbochargers here, and I'm going to talk about those. We'll start with our engine components. So for those of you who have been following us for a while, you'll know that we do have a range of engine building courses, and we're about to embark on another engine build that's going to be added into our library of worked examples in that course. Specifically, we are going to be adding in a Mitsubishi 4G63 worked example. So I'm going to show you through those parts actually before we do that though. For anyone who has maybe been living under a rock and hasn't followed us for that long, let's just head across to my laptop screen and I'll just quickly show you sort of where my personal background was. And this is my old shop car back on our Instagram page. This is a Mitsubishi Lancer Evo 3, and this was a shop car I built up for my old business, STM or Speed Tech Motorsport. I built this up from a road car and basically wanted to go drag racing, and I built this up at the time I started my business. All I really wanted to do at that time was run a 10-second quarter mile, and obviously looking at the tube frame front end, it progressed a little bit beyond that. I'll talk about that in a moment. It ran a 10-second quarter mile on its second pass ever down the drag strip, so it was a bit of a sort of a underwhelming effort really. Didn't actually turn out to be that hard. I think I ran a 1088 or a 1089 on its second pass down the strip. Now, let's be honest, today a 1080 is not really anything to be too excited about. Still makes for a very fast road car, but these days times have well and truly moved on. I got pretty well stung by the drag racing bug though, and kind of went crazy with the car over the next few years. It turned out to be the perfect learning platform for me, developing both my engine building skills on the 4G63 platform as well as my tuning skills, and it gave me a chance to really compete on the world stage. At the time that car was retired, which looks a bit like it does in the picture you're looking at on the Instagram page there, it held the outright world record for the Mitsubishi Evo 4G63 four-wheel drive platform. At that time, that record was held at 8.23 at 180 mile an hour. I'll just clarify, this is the Evo platform. John Shepherd was a little bit quicker in his Talon Eclipse, just for those who want to pull me up on technicalities there. But yeah, 823 at 180 mile an hour. Yeah, there's a bunch of people now in the sevens, but this was probably back, I want to say probably a good 12 years ago now. So this car was actually still on the top 10 list up to about a year or so ago, I believe. At the time that was retired, it was making around about 1170 wheel horsepower, running 54 psi of boost on methanol fuel. And we also revved the engine out to 10,500 RPM on every shift. Bearing in mind here as well, we were still running a cast iron block. The availability of billet parts, which is so prevalent these days, just wasn't out there. So understandably, learning how to basically keep an engine together under that sort of power and RPM stress took a little bit of time. We also developed what we learned on our own platform, and this filtered down to our drag engine program, which we had for a number of our customers. So speaking of which, just to sort of show what else we're involved with, at the time I built this Mitsubishi Evo 9 with the help of the rest of the crew for one of our customers, and at the time this was retired, this held the late model Evo four-wheel drive record. The US market seems to be a little bit fussy about Evo records. They kind of disregard the Evo 1, 2 and 3 because they never got them there. 1, 2, 3 and 4 I think. Anyway, basically 7 to 9 is what they class as an Evo. So we wanted to prove again that we're on an even footing with the best in the world. So at the time, AMS Performance in the US held the Evo record with a 8.420. We smashed that record, and in the end this car went as quick as an 8.34 at 170 mile an hour. Again, times have moved on. What is important to mention about this particular engine was we weren't actually aiming for peak power. The reason for this, for for a class rule, we're actually limited in the size of the slick we could run. So it wasn't actually much point us making 12, 13, 1400 horsepower because it'd just go up in smoke. So really, with this car, we focused solely on trying to get all of that power to the track as efficiently as we could. So we actually only ended up making 1001 wheel horsepower in that engine. Obviously, still, we're not messing around there. 1000 horsepower from a 2.2 litre four-cylinder is still pretty serious, but nothing like the sort of power figures we see. All right, so that's the background there. Just to show I've got a few credentials in the 4G63 world. We have been asked for the whole time we've been doing engine building courses about 4G63 worked examples or content in general. So that's what we're doing. We're actually going to be purchasing a Evo 9 shop car a little bit later this year when we retire our trusty Subaru STI. So we're actually getting a little bit ahead of the game with a build for that engine. So let's start by showing you this crankshaft. So with the 4G63, let's get it under the overhead so you can sort of see what we're looking at here. So this is a billet crankshaft from Manly. And it's not necessary to strictly go to a billet crankshaft for the sort of power levels that we're aiming for. This will be in the region of about maybe 700 flywheel horsepower absolute max. And the factory crank, I've well proven that can go over 1000 horsepower. So billet crank in itself, not an essential item. However, what we wanted to do was increase the engine capacity slightly. There's a real big limit to what we can do in terms of bore to increase the capacity on the 4G63. There's not a lot of material between the adjacent bores, so we can't really go out, well, I don't personally like to go out more than 20 thousandths of an inch or half a mil oversized, so that's not really going to cut it. The factory crankshaft has an 88mm stroke, so 88mm stroke along with a 85mm bore gives us the 2 litre capacity. There are also 100mm stroke cranks that come out of the factory 4G64. Very, very popular upgrade. So by using the 64 crank with a 100mm stroke in the 4G63 block, we get to 2.3 litres. Or alternatively, you can use the 64 block, which has a larger 87mm bore. So the 4G64 block, either way we go there, there's options. There is also a deck height difference between the blocks. I don't dislike the 64 block, but it does, or the 64 crankshaft, but it does affect our rod to stroke ratio. It does affect the engine's ability to rev, which is one of the nice features with the 4G63. So what we're going for is a bit of a compromise here. This billet crankshaft is a 94mm stroke, so it sits nicely in between the 88mm and 100mm stroke. So that will get us out to 2.2 litres. It still works really nicely in a 4G63 block. It does still negatively impact on our rod to stroke ratio, but it is workable, and I've well proven that this is essentially the same style of crankshaft that was in the Evo 9 that I just showed you. Now just a little bit about billet versus forged. So there's a lot of talk about this, a lot of misinformation out there as usual. What we actually find is that most of the common and popular Japanese performance engines, along with a lot of the US domestic market engines, do come with a forged crankshaft. And this is in comparison to the older style of cast crankshaft. Cast crankshaft, not a good mix for a performance engine because there isn't any real grain structure. There's not a lot of strength in the crankshaft and the way it's manufactured. Essentially, it's just a mold that molten cast iron is poured into, and it's allowed to cool. So a cheap way of producing a crankshaft, but again, not a lot of strength, so not good for us in terms of a performance application. So the forging technique, again, that's been used in OE production for a fair while, as well as aftermarket crankshafts. That basically forces the crankshaft material, in a raw piece of material under immense heat and pressure, into the shape of a crankshaft. So that gives us a grain structure, it gives us a higher density to the material as well, so that improves strength. So billet, on the other hand, actually doesn't have that same advantage with the grain structure that we get with a forged crankshaft. So in some ways, in many ways, the forged crankshaft is a superior option. Why billet crankshafts have come to be very popular is that it is a more cost-effective way of making a small run of crankshafts, taking a large billet of the material you want to use for the crankshaft and machining it down into a crankshaft. Much cheaper than basically going through the process of forging forging for a small run of crank. So still totally acceptable, very, very strong crankshaft, not something that's going to give us issue, but I do hear people sort of assuming that the billet crankshaft is stronger than a forged crankshaft, and it's just important to say that that's not necessarily the case, and there are a lot of factors that go into this, including the material as well as the actual design of the crankshaft. So that's step one. Step two, we are also going to go with a stronger piston. The factory 4G63 pistons, there's nothing specifically wrong with them. They're actually pretty strong, but they are cast. They do require a little bit of care with the tuning, particularly when you start increasing the cylinder pressure, boost pressure and power. So we're going with a JE forged piston. I'll just get this under the overhead. Nothing particularly special here. We have decided to cap our compression ratio at 9:1. This will be a flex fuel engine, so when we're aiming for big power, we will be on E85, but we still wanted to be able to run it on pump gas, so it's important not to pump that compression ratio too high. You can see we've got a heat reflective coating on the crown, and we've also got an anti-friction coating on the piston skirt, so nothing particularly unusual there. One of the considerations as well, when we are choosing a piston style, there are a variety of different styles. JE, just as one manufacturer, offer a asymmetric piston skirt design, which is designed to reduce the frictional losses against the cylinder wall, which is absolutely great in the right application. As we start punching the power levels higher and higher though, the additional frictional loss from a full round or a symmetric skirt like the one we've got here is probably more beneficial than the potential reduction in strength. So that's why we've got a symmetric skirt design there. Last part of the puzzle, nothing particularly exciting here. We are going to be running a set of boost line connecting rods from Wiseco. We'll get that under the overhead here. This isn't actually a rod that I have personally had any experience with. I've only heard and seen good things from them. They certainly are a nice beefy design to the rod, so I'm looking forward to seeing how they work once we get them all built. So there's a few tricks with the 4G63. It's not a particularly complex engine. One of the areas that we will be focusing on a fair bit of detail is the lubrication system, particularly around the balance shafts in the engine. This is a common modification to remove those balance shafts, and absolutely we do this with all the 63s that we build. But there are a variety of ways of removing those balance shafts, and we're going to focus on why we don't want to be cutting off the stub shaft out of the back of the oil pump, which is very, very common, and we'll show you how we can do that with a machine down balance shaft instead with the counterweights removed off it. Some other aspects around the cylinder head sealing, so we'll show you a few of the tricks and tips that we've learned over the time from our drag racing program as well, and some of the modifications we can make to the sump, so how we can get the best possible results from a conventional wet sump without the expense of going to dry sump lubrication. So that is going to be started hopefully in the next week or two, and we'll probably have that worked example out in the next sort of few months, just as soon as we can get onto it. A lot of other stuff going on around here as well, and one of those other projects we are working on is our SR86. So if you've been following us for the last few weeks, you'll know that we did get it back to the track. Had a really good weekend of racing, which was quite refreshing after the problems that car has given us. It's showing a lot of promise. We have got a 1 hour shakedown test scheduled for about 2 weeks time. So it'll be a private test day where we're just going to put the car through its paces for a full hour of racing, and basically see that all of the cooling systems are capable of keeping up, because that was one of the big areas we found problems. However, it all wasn't plain sailing. We did go from the Calford cam back to a Nissan factory P12 cam to try and gain some bottom end response. That did prove to be effective to a point, but we were still seeing a slightly more lethargic boost response than I'd like. So the turbocharger that we have been running is this guy here. This is a Garrett GTX 3076R Gen 2 turbocharger, and we're running this with a 0.83 AR rear housing on it. And I got asked by quite a few people, why did we choose this turbocharger when Garrett had their new G series available even back when we started the project? Fair enough. There is usually some kind of method in our perceived madness though, and at the time, and admittedly this project has taken probably about a full 2 years longer than we had hoped. Just like everything, it takes longer than you'd expect. We weren't really seeing a lot of hard data on a comparison back to back between the original GTX turbochargers and the newer G-Series turbochargers, and we wanted to provide that information and wanted to do it in our usual over-the-top way with a bunch of data rather than just running the car on the dyno, getting 2 back-to-back results with the different turbos and calling it done. So that was the plan all along, and we are now pulling the pin on doing that. So over here on the workbench, and we'll get this under the overhead camera, we've got a GTX G20, sorry, not a GTX, a new Garrett G25 660 turbocharger with a 0.92 housing. I'll actually try and get this side by side because it is quite apparent just how much smaller it is compared to the older GTX. Now on paper, despite the fact that this guy is significantly smaller, the outright flow capability is not too much different, which at the moment, I must admit, I'm finding a little bit hard to believe, but the dyno will tell us what that actually pans out to be like. Ultimately, I'm not actually that worried about outright power though. For endurance racing, it's likely we will run this engine probably around about the 450 wheel horsepower mark. It's plenty fast enough at that point. We're not really leaning on the engine too hard, which is exactly what you want for endurance racing. It's for sprint racing where we will want to turn it up. With the old GTX 3076, we had seen 650 wheel horsepower and about 26 psi of boost. Probably not expecting to quite see that with the G25 660, but let's give it a red hot crack and we'll see what that pans out like. So once we've got the car back up and running, we're going to re-dyno it with the GTX 3076. We're going to do some power runs at 15, 18, maybe 22 and 24 psi just to get a really good spread of how that turbo performs. We've got a lot of data on that car, including turbo speed, compressor inlet and outlet pressure and temperature, turbine inlet pressure, exhaust gas temperatures, etc. So it'll give us a really good data set to see how the GTX 3076 stacks up, and then of course we'll swap over to the G25 660, rerun all those tests and see exactly what we've got. We're hopeful that we're going to gain a reasonable amount of bottom end response, possibly at the sacrifice of a little bit of top end power. And again, absolutely fine with that. At the moment, we're only running the GTX 3076 at about 1 bar boost, 15 psi to make 450, 460 wheel horsepower. So if we end up sacrificing 10 or 20 horsepower in the top end, I can easily drag that back with another 1 or 2 psi of boost pressure. But for us, the benefit in the faster response that we're hopeful we're going to see will far outweigh any disadvantage we have in terms of the top end power. So we'll be getting some information on that coming out as soon as we get an opportunity. We will be making a full video about the results there for our YouTube channel. So if you aren't subscribed already, please make sure you do so. Now we've got a bit of an engine theme going on at the moment, so we'll jump across to my laptop screen for a second here, and I just wanted to talk a little bit. I was actually a bit more prepared for this. I'll grab this while we're talking. The engine on the screen at the moment, there is a Subaru FA20, or half of a Subaru FA20, and we just jump to our overhead. Hopefully haven't thrown Sam under the bus too much because this is probably out of focus, but it's okay. I just want to really demonstrate what an open deck block is for those who aren't aware. This is the FA20, one of our FA20 engines, and we can see the water jacket right through here. Basically, the inner part of the cylinder is completely detached from the outside. This is pretty common. It's called an open deck block, and the reason manufacturers do this is it's much cheaper to cast the block with this design. The processing for actually casting the block is much simpler. That's absolutely fine for a factory engine. In fact, we've been running this exact style of open deck FA20 up to about 380 wheel horsepower for our other 8.6 race car. But you get to a point where the cylinder pressure increases so much that the sleeves can actually move around, they can crack, can cause head gasket failures and problems. So a solution which it is a little hard to see, but given that you've just seen what a FA20 normally looks like, you can hopefully see that if I just trace around this, there's actually what's referred to as a deck plate that has been machined, and it's an interference fit into the block. So basically that deck plate is around about a 8mm thick alloy plate. It's been CNC machined to precision. The block is then CNC machined as well to get about a 1 thou to 2 thou interference. That deck plate is then press fit into the block. It obviously links then the inner sleeves to the outside of the block, giving a lot more rigidity at that deck surface, and then it's simply skimmed flat as part of the decking process when the engine is machined. So it's just a nice way of adding some additional strength to an open deck block. It's not the only way of doing it, but it is a nice solution. We've actually got a deck plate that Zach, our wiring tutor, made for us in-house. So we've got an FA20 engine going together in the not too distant future that's going to take advantage of that process. And actually down the bottom of this picture, you can actually see one of those deck plates that is actually hanging off the ARP studs there to get a better perspective of what that all looks like. It is a bit of a balancing act. Obviously, we still need to maintain sufficient coolant flow through the deck plate from the water jacket up into the cylinder head as well. So it's not just a case of blocking everything off and keeping your fingers crossed. There is a little bit of science that goes into getting this right. Right, just give me a moment here. I'll head back across to my notes. Now, podcast as well. If you've been following for a little while, I've been mentioning this just about every time I've done one of these webinars. We have launched our HPA Tech Talk podcast. So if you are looking for a simple way of digesting HPA content, this is going to be for you. We'll jump across to my laptop screen again. You can check out hpatechtalk.com. A bit of a play on words there. Talk, of course, is TORQUE. I know, it's hilarious. We release a new episode every Tuesday. Our latest release is engine block design. We're talking cast versus billet. This is an interview that we did with David Mountain from Mountune over in the UK back a couple of years ago when we were allowed to travel. So, and specifically here, we talk with David about what goes into the design of some of their engines that competed in World Rallycross. And these engines, on face value, you might not think are under a lot of stress. The World Rallycross engines only make about 600 horsepower. However, the part that's easy to overlook is the immense amount of cylinder pressure they generate because of the high boost pressure they run at relatively low RPM due to the restrictor. So if you are interested in learning a little bit more about that, check out HPA Tech Talk. You'll find that our podcast anywhere you normally listen to podcasts. Now, also latest release as well on our YouTube channel. So we'll just head over there and have a quick look. So one of the problems we see, particularly when we are degreeing cams, or alternatively when we are finding true TDC for timing an engine in terms of the ignition timing, finding true top dead center and understanding what that means. So this is basically finding out accurately when the piston is at exactly the top of the stroke. It's not very difficult, but there are some ways to do it correctly and there are some ways to do it incorrectly. So there's a bit of a lesson there. If you do want to learn how to do that, head across to our YouTube channel. If you like that video, give us a thumbs up. Subscribe while you're there if you haven't already, and if you've got any questions on that video, make sure you ask them. Right, I think we are just about done for today. So thanks to everyone who has been watching. Give me a few moments here and we'll get started with today's lesson.
If you like that video, make sure you give it a thumbs up. And if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.